Last time we proved that a square matrix is invertible if and only if its reduced row echelon form is identity. A rectangular matrix which is not square is never invertible. Today, we are going to find a computational procedure for finding an inverse of a square matrix. We begin with the following definition. A matrix is called elementary if it is obtained from identity matrix by applying a single elementary row operation. So thus, we obtained a correspondence between elementary row operations and elementary matrices. So to each elementary row operation, we associate one elementary matrix, which is obtained from identity matrix by applying that particular elementary row operation. Let us look at some examples. We have three types of elementary row operations. And so this gives us three types of elementary matrices. So type 1 is the following elementary row operation. So when we take a row and replace it by a sum of that row plus a multiple of another row. Right. So let's consider an example. So suppose we have 3 by 3 matrices, and so let's say that row 3 new is row 3 plus c times row 1. Now, what is the corresponding elementary matrix? Well, we start with identity matrix of size 3 by 3. And so this is identity. And we apply this particular elementary row operation. So the first two rows are unchanged. So we have 1, 0, 0, 0, 1, 0. And the last row is row 3 plus constant times row 1. So then this will give us the following row. So this is the elementary matrix that corresponds to this particular elementary row operation. So then we have type 2 elementary row operation. So when we multiply a row by a non-zero scalar, so we have k times row I, and so here k is a non-zero element of our field. So for 3 by 3 matrices, so let's consider the following. So row 2 prime is k times row 2. So if we take this identity matrix and multiply its second row by 2, then we get the following elementary matrix. So 1, 0, 0, 0, k 0, and 0, 0, 1. So this is an elementary matrix that corresponds to this elementary row operation. And finally, we have type 3 elementary row operation, where we switch two rows. And for our example, so if we switch row 2 with row 3, so we take identity matrix and we switch the last two rows. And the matrix that we get is the following: 1, 0, 0, 0, 0, 1, and 0, 1, 0. So we see that given an elementary row operation, we can easily construct the corresponding elementary matrix. Our method for matrix inversion is based on the following key observation. Applying an elementary row operation to a matrix A is equivalent to multiplying A on the left by corresponding elementary matrix. So what we say here is the following. So if we take a matrix A and apply an elementary row operation to it, and so we get the matrix A prime, then this matrix A prime can be expressed as a product E times A, where E is the elementary matrix corresponding to this particular elementary row operation. Let us verify this observation. So we'll begin with type 2 elementary row operations because this is probably the easiest case. So we take and say that row I prime is k times row I, and all other rows are unchanged. Now, what is the corresponding elementary matrix? Well, so we take identity matrix and we multiply row number I by a non-zero scalar k. So then what we see is, so all other rows will be unchanged except for row I, so where we're going to get entry k on the diagonal, and elsewhere we're going to get ones on the diagonal. So this is, here we have, this is in row I. And now let us consider this product. Let's take an arbitrary square matrix and multiply it by this elementary matrix. So let us see what is going to happen. So if we have so E times A, so we get so this matrix where we have K in row I, and so we have this matrix A here. Now let us see. So how do we obtain the result? We know that an entry in row P and column Q of the result is obtained as a dot product of row P in the left factor and column Q in the right factor. So if we want to calculate here first row, then we need to take the first row in the left factor, and we need to compute dot products with all the columns in the right factor. Right? And so what we're going to see is, as a result, so these dot products will pick out the first entries in these columns, and essentially we're going to get row 1 of matrix A as the result here. So when we take the dot product with the second row, right, so that has 0 and 1 in this position. So then when we do the same thing, we're going to pick out second components in each column. And so this will be row 2 of the resulting matrix. And so this pattern will repeat until we come to row I, right? So this is in row I. And when we take the dot product of this row with each column of matrix A, then we are going to pick ith entry in each column multiplied by this non-zero scalar k. And so this means that in row I, we're going to get k times row I of matrix A. And so all other rows will be unchanged. And what we see is that as a result, we get a matrix that is obtained from matrix A by multiplying row number I by non-zero scalar k. But that's exactly applying this elementary row operation. Now let us look at type 1 elementary row operation. So we say that row I prime is row I plus c times row j. Now, what's the corresponding elementary matrix? So we take the identity matrix, and so we change row I in this matrix, right? So by adding c times row j. So what we're going to get is we get ones on the diagonal, and now in row I, we're going to get entry C, which will be in column J, right? So because if we take row J, then row J will have 1 on the diagonal with in position number J. So when we add to row I C times row J, so then this scalar C will appear in row I in column J. So we're going to write this elementary matrix as an identity plus the matrix F, where F is just so the matrix that has entry C in row I and column J and zeros elsewhere, right? So we have zeros on the diagonal and elsewhere as well, right? So what we do is we take this elementary matrix and just split it as identity matrix, which captures the ones on the diagonal, plus the matrix F, which captures this off-diagonal element. Now let us compute what is the product E times A in this case. Well, E can be written as I plus F times A. And so this can be expanded. So this is I times A plus F times A. I times A is just A. So what we get is A plus FA. So what we need to compute is we can compute just the product F times A. So let's do this. So we have F times A is the following product. So here we have a matrix C where we have entry C in row I and column J. And we multiply this by matrix A. And again, so what we see is that we multiply rows of the left factor with columns of the right factor. And in matrix A, all rows except for row I are 0 rows. So this means that here we're going to get 0 rows, all except for row I. And so when we calculate row I of the product, so what we do is we take this row, which has all zeros except for scalar C in position J, and when we multiply with the first column, so this will pick out entry number J in the first column, multiply by the constant C. So then this will go in row I, column 1. And then when we multiply this row by the second column, so we will get C times entry J of the second column. And so what we see is that the row I of the product will be C times row J, because we pick out jth entry in each column. So this will correspond to row J of the matrix A. And so this will be recorded in row I of the product, right? So what we get that all rows of F times A are 0 except row number I, right? So this will be row I of the product, which will be equal to C times row J of matrix A. And if we add this matrix to matrix A, so then we see that in this sum, all rows except for row I are the same as the corresponding row of matrix A. And for row number I here is, so we get row I of matrix A from this summand, and from F times A, so what we get is we get C times row J of matrix A. And so what we see is the confirmation of our claim that multiplying by this elementary matrix, so by this elementary matrix on the left, is equivalent to applying the corresponding elementary row operation to matrix A. And for type 3 elementary row operations, so I leave verification of this claim for you as an exercise. Let us prove the following theorem. Let A be an invertible n by n matrix. Consider a sequence of elementary row operations that brings A to identity matrix. Then the same sequence of elementary row operations will bring the identity matrix to the inverse of the matrix A. We know that invertible n by n matrices are characterized by the property that their reduced row echelon form is the identity matrix. And so if A is invertible, we know that there is a sequence of elementary row operations that brings A to its reduced row echelon form, that is to identity matrix. So this sequence will exist. And then if we take this sequence and apply it to identity matrix, then the claim of this theorem is that the result will be A inverse. So let's give a proof. So let E1 through EK be elementary matrices that correspond to the given sequence of elementary row operations. So we know that for each elementary row operations, we have the corresponding elementary matrix. And performing each of the elementary row operations may be interpreted as multiplication by the corresponding elementary matrix on the left. So this row reduction of A may be interpreted in the following way. So we start with the matrix A. So applying the first elementary row operation is equivalent to multiplying by E1 on the left. Applying the second elementary row operation corresponds to multiplying the result by the second elementary matrix on the left. And if we continue this, so we have iterated multiplications by these elementary matrices. The last factor will be EK. And the result of this process is the row reduction of A. So this means that this process brings A to identity matrix. So this product is equal to identity matrix. Now, let us apply the same sequence of elementary row operations to identity matrix. So in terms of elementary matrices, this can be written as a product. So instead of starting with matrix A, we start with identity matrix. And we multiply identity matrix by the sequence of elementary matrices. This theorem claims that the result of this computation will be the inverse of the matrix A. Now, for now, let us call this matrix B. So we need to prove that B is equal to A inverse. Now, let us look at the first equality. So here, applying the associative law, we can group our factors on the left in the following way. And then we see that this first factor is precisely our matrix B. So this first equality can be written as B times A is equal to identity. But then this says that B is the left inverse of A. So the definition of the left inverse is precisely this. So if we multiply matrix A on the left by matrix B, then B, and the result is identity matrix, then B is the left inverse of A. Recall that the assumption of this theorem is that A is invertible. And in the previous lecture, we proved that if we have an invertible linear transformation, then its left inverse is equal to the full inverse of this transformation. And the same arguments apply to matrices as well. So here we have A is an invertible matrix, B is the left inverse of A, and from here we conclude that B is equal to A inverse. And so that's exactly what we need to show. So we obtain that if we take the identity matrix and apply the same sequence of elementary row operations that brings A to identity, then the same sequence will bring identity to the A inverse. And this completes the proof of this theorem. The importance of this theorem is that it gives us an algorithm for computing the inverse of an invertible square matrix. So to compute A inverse, write A side by side with the identity matrix I. Then use elementary row operations to bring A to its reduced row echelon form, which is the identity matrix. So this will be its reduced row echelon form. Apply these elementary row operations to both matrices. The resulting matrix on the right will be A inverse. So basically what we do is we write the matrix A, and next to it as kind of an augmented matrix, but now with not a single column, but with the whole matrix, we write matrix I. And then we apply elementary row operations. So we do row reduction for matrix A that brings A to its reduced row echelon form. And so the reduced row echelon form of A is going to be the identity matrix if A is invertible. And once this happens, then on the right, we are going to get A inverse. Right? So remark, if reduced row echelon form of A is not the identity matrix, so that is has 0 rows, then A is not invertible. Right. So if we fail to bring A to identity matrix, then this means that the matrix A does not have an inverse. So whenever the inverse exists, so this algorithm will compute it. And if this algorithm fails, then the inverse does not exist. Let us consider some examples. So let's start with a 2 by 2 matrix. So let's take A to be the following matrix. So 1, 2, 4, 6. And we want to find A inverse. So what we do is we write A side by side with the identity matrix. And this identity matrix also has size 2 by 2. So we get the following matrix: 1, 2, 4, 6, and 1, 0, 0, 1. So now we want to find the sequence of elementary row operations that bring the left matrix to identity. So then our theorem says that the same sequence of elementary row operations will bring the right matrix to A inverse. So now let's apply our elementary row operation. So now we want to erase the entry here. So we say that row 2 new is row 2 minus 4 times row 1. And we apply this elementary row operation to both matrices. So we get 1, 2, 1, 0. So the first row is unchanged. For the second row, so we are going to get 0 here, and 6 minus 8, that's negative 2 here. And so if we take row 2 and minus 4 times row 1, we get minus 4 and 1 here. So now we want to create a pivot in this second row. So to do this, so we multiply second row by negative 1/2. And the matrix will become, so 1, 2, 1, 0. And so here we get 0, 1, and multiply by negative 1/2. So this will become 2 and negative 1/2. And now the last step is to create a 0 above the second pivot. So what we say is row 1 new is row 1 minus 2 times row 2. Now, so what we get is 1, 0, and so here we subtract 2 times row 2. So 1 minus 4, that's negative 3, and 0 minus 2 times negative 1/2, that becomes plus 1. And we have 0, 1, 2, negative 1/2. And by our theorem, so once the left half became the identity matrix, the right half will become the A inverse. So this tells us that A inverse is the matrix negative 3, 1, 2, negative 1/2. It's always a good idea to verify that we did not make an arithmetic mistake in our calculation. So let's just compute A times A inverse. So here we have A is 1, 2, 4, 6. And our answer for A inverse is negative 3, 1, 2, negative 1/2. So let's multiply these two matrices. So we take the first row and take the dot products with the first column. So we have negative 3 plus 4. That's 1. Now we take the first row and take the dot product with the second column. So we have 1 and plus 2 times negative 1/2. So that's 0. Now we take the second row, 4, 6, and take the dot product with the first column. So 4 times -3, that's -12. 6 times 2, that's +12. So we get 0. And finally, the dot product of second row with the second column is 4 minus 3. That's 1. And so what we see that indeed, so the result is the identity matrix. And this confirms that we did not make any arithmetic mistakes when carrying out this computation. Next, let's compute an inverse of a 3 by 3 matrix. So we take this matrix and write the identity matrix next to it. And now we need to find the sequence of elementary row operations that brings the left matrix to identity. So first I want to create a pivot in the corner. So what we're going to say is that we say row 1 new is 1/2 of row 1. So this gives us 1, -1/2, 0, 1/2, 0, 0, and then 0, 2, 3, 0, 1, 0, and 3, 2, 5, 0, 0, 1. So then we need to eliminate this 3. So we say that row 3 new is row 3 minus 3 times row 1. Our resulting matrix is 1 minus 1/2, 0, 1/2, 0, 0, then 0, 2, 3, 0, 1, 0, and here we have 0, then 2 minus 3 times -1/2. So it's 2 plus 3 halves. So we have 4 halves plus 3 halves, so that's 7 halves. And 5. And so here we get -3 halves, 0, 1. So next we create a pivot in the second row. So we say row 2 prime is 1/2 times row 2. We get 1 minus 1/2, 0, 1/2, 0, 0, 0, 1, 3 halves, 0, 1/2, 0. And here we have 0, 7 halves, and 5. And -3 halves, 0, and 1. So now we eliminate 7 halves. So we say row 3 new is row 3 minus 7 halves times row 2. We get the matrix. 1 minus 1/2, 0, 1/2, 0, 0, 0, 1, 3 halves, 0, 1/2, 0, and 0, 0, then 5 minus 3 halves times 7 halves. So this product is 21 quarters, and 5 is 20 quarters. So we have 20 over 4 minus 21 over 4. So we get -1/4. And so here we get -3 halves. And so we have 0 minus 7 halves times 1/2. So this is -7 over 4 and 1 here. Now to create a pivot in the last row, we multiply the last row by -4. So we say row 3 new is -4 times row 3. So we get 1, -1/2, 0, 1/2, 0, 0, then 0, 1, 3 halves, 0, 1/2, 0, and 0, 0, 1. So we get negative or positive 6 rather. Then we have 7 and we get negative 4. So for the next step, so we say new row 2 is row 2 minus 3/2 of row 3. So then we get 1 minus 1/2, 0, 1/2, 0, 0. Then here we get 0, 1, 0. So we have 0 minus 3/2 times 6. So this is negative 9. So then 1/2 minus 3/2 times 7. So this is 7 times 3/2 is 21/2. So 1/2 minus 21/2. So this is negative 20/2, which is negative 10. And so here we have 0 minus 3/2 times negative 4. 3/2 times 4, that's 6. And so we get plus 6. And 0, 0, 1. And here we have 6, 7, negative 4. And our last elementary row operation is row 1 new is row 1 plus 1/2 of row 2. So then we get identity matrix in the left hand side. And so now we have, so we add half of row 2. So here we have half of negative 9. So this is negative 9/2 plus 1/2. So that's minus 8 over 2. So that's negative 4. Then here we have negative 1/2 times negative 10. That's positive 5. And negative 1/2 times 6. That's negative 3. And 0, 1, 0. So here we have negative 9, negative 10, 6, and 0, 0, 1. So we get 6, 7, negative 4. So this tells us that A inverse is the following matrix. So negative 4, 5, negative 3, negative 9, negative 10, and 6, and 6, 7, 4. Finally, it would be a good idea to check that A times A inverse is the identity matrix, so that to ensure that we didn't do any mistakes in arithmetic. And I leave it up to you to do. Inverse matrices may be used for solving systems of linear equations. So let us state the following result. So let AX equals B be a system of n linear equations with n unknowns with invertible matrix A. Then this system has a unique solution which may be found as X equals A inverse times B. And so for the proof of this theorem, we know that a system of linear equations can be interpreted as a matrix equation. So here we have a product of a matrix A with an unknown vector x is equal to B. And we can just interpret this as a single algebraic equation involving product of a matrix with an unknown vector. And so then what we can do is we can just multiply both sides on the left by A inverse. So since we know that A inverse exists, so we can do it. And so now we get a new expression. So if this holds, then A inverse times A times x is equal to A inverse times B. But how can we express the left-hand side? So in the left, since we know that this multiplication is associative, so A inverse times A is equal to identity. So we have identity times x. And identity times x is simply equal to x. And as a result, we get that x is equal to A inverse times B, right? And this clearly tells us that there is one solution, and this solution is given by this product. Now, we should point out that this method of solving systems of linear equations is not necessarily efficient, because it is actually easier to solve a system of linear equations using Gaussian elimination rather than compute the inverse of a matrix. But there are situations when we already know what's the inverse of a matrix. So then this will become a very efficient method. So instead of doing Gaussian elimination, if A inverse is already given to us or known, then by taking this product, we immediately obtain the solution. Another situation where this could be effective is suppose we want to solve many systems of linear equations with the same coefficient matrix, but different right-hand side columns. So this also comes up in applications. And again, in that situation, rather than solving many systems of linear equations using Gaussian eliminations, we can once compute the inverse of a matrix and then find solutions to all these systems by multiplying the inverse of the matrix by the corresponding right-hand side column. Next, let us look at more matrix equations. Problem. Solve matrix equation x times 1, 2, 2, 3 is equal to 5, 10 minus 1 minus 2, where x is an unknown 2 by 2 matrix. So here, this equation looks like this. So it's x times a is equal to b. So if a is invertible, we can solve this in the following way. So we multiply both sides by A inverse on the right. So then this will become x times A inverse is equal to B times A inverse. So keep in mind that it is important on which side we are multiplying. And so this, because multiplication is associative, so we can group this product in this way. So then we get x times identity, which is simply equal to x, and we get b times A inverse. And we see that if A is invertible, then this matrix equation has a unique solution, which is the product of a matrix B with the inverse of a matrix A. So now we find A inverse. So we take the matrix 1, 2, 2, 3 and write the identity matrix next to it. And then we do row reduction. So we say that row 2 new is row 2 minus 2 times row 1. So we get 1, 2, 1, 0. And 0, 3 minus 4, that's negative 1. And we get minus 2, 1 here. So then we multiply the second row by negative 1. So row 2 prime is negative row 2. So this gives us 1, 2, 1, 0, 0, 1, and 2, negative 1. And the last step is row 1 prime is row 1 minus 2 times row 2. And so here we get identity matrix on the left, and on the right we get 1 minus 4, that's negative 3. Then 0 plus 2, that's 2, and 2, negative 1. And so this tells us that A inverse is the matrix negative 3, 2, 2, negative 1. Right? And if we multiply these two matrices, so let's quickly check. 1, 2 dot product with negative 3, 2, that's 1. 1, 2 with 2, negative 1, that's 0. 2, 3 with negative 3, 2, that's 0. And 2, 3 with 2, negative 1, that's 4 minus 3, that's 1. So the product of A and A inverse is indeed identity. And finally, we calculate the answer. So we know that X is B times A inverse. So we saw that matrix A is invertible. So the matrix B is 5, 10, negative 1, negative 2. And A inverse is negative 3, 2, 2, negative 1. And so the matrix X is 5 times negative 3, that's negative 15, plus 20, so that's 5. 5 times 2, that's 10, minus 10, that's 0. So here we have 3 minus 4, that's negative 1. And we have negative 2 plus 2, that's 0. Now let us change this problem a little bit. So now let us solve the following equation. So X times 1, 2, 2, 4 is equal to, well, I'll take the same matrix in the right hand side. 5, 10, minus 1, minus 2. Now, can we use the same solution here, right? So it turns out that we can't, because this matrix A here that we inverted in the previous example is no longer invertible. So indeed, when we do row reduction, so we see since the second row is 2 times row 1, so then reduced row echelon form of A will have a 0 row. So this means that this method will not work in this case. Now, can we solve the problem? Yes, we can, but now we have to use a different method. So here we should write the unknown matrix with unknowns x1, x2, x3, and x4. Then what is x times A? So this is the product, x1, x2, x3, x4 with the matrix A, 1, 2, 2, 4. So let us write down this product. So we take dot products of rows with columns. So we have x1 plus 2x2. Then with the second column, we have 2x1 plus 4x2. Then in the second row, we get x3 plus 2x4 and 2x3 plus 4x4. And this must be equal to B, so which is the matrix 5, 10, minus 1, minus 2. So this gives us a system of 4 linear equations. So x1 plus 2x2 is equal to 5. 2x1 plus 4x2 is equal to 10. Then x3 plus 2x4 is negative 1. And 2x3 plus 4x4 is negative 2. So then we can construct a system of a matrix of this system of linear equations. So we have 1, 2, 0, 0, right? So now we have 4 equations and 4 unknowns. So the right hand side is 5, 2, 4, 0, 0, and the right hand side is 10. Then 0, 0, 1, 2 is negative 1, and 0, 0, 2, 4 is negative 2. So now we do row reduction. So we say row 2 new is row 2 minus 2 times row 1. So we get 1, 2, 0, 0, 5. And the second row will disappear. And 0, 0, 1, 2, negative 1. And 0, 0, 2, 4, negative 2. And we say now that row 4 new is row 4 minus 2 row 3. So, and then the last row will disappear. So we get 1, 2, 0, 0, and 5. 0, 0, 0, 0, 0, 0, 1, 2, negative 1, and 0, 0, 0, 0, 0. Right. So now if we switch rows 2 and 3, we're going to get the reduced row echelon form. And so let us now see that, okay, so we have 2 pivots here. So this means that the variables x1 and x3 are leading, and the variables x2 and x4 are free. So we assign parameters to free variables. So we say that x2 is equal to s, and x4 is equal to t. Then x1 is equal to 5 minus 2s, and x3 is negative 1 minus 2t. And so then we can write down our matrix X. So we want to write down the general solution. So X is going to be the following matrix. So it's 5 minus 2s, then s, and minus 1 minus 2t, and t. And so here s and t are, well, if this is over the field of real numbers, then these are arbitrary real numbers. And so what we see is that in the second case, right, so for this matrix equation, we actually get infinitely many solutions. So we have a 2-parametric family of solutions, where when the matrix A was invertible, then clearly this would tell us that the solution will be unique. I want to finish this lecture with some exercises that I leave for you to solve. 1. So let A be an n by m matrix and B be m by k matrix. show that every column of the product A times B is a linear combination of columns of B. And every row of A times B is a linear combination of rows of A. So the second problem, show that rank of A times B is less or equal to a rank of B, and also that rank of A times B is less or equal to a rank of A. And the last problem, so let A and B be two n by n matrices, so that is square. Suppose A times B is equal to identity. Show that B times A is also equal to identity. And is the same true for non-square matrices. So this means that if A is of size n by m, and B is a matrix of size m by n.